I'm Dr. Aaron Tucker. I am in the English department. I always like to start this talk with this image here of these adorable cats playing chess. It was one of the first images that I saw pretty early on. You can see 2022, where I felt like generative AI was starting to be more of a public discussion. This image comes from an article in the New York Times. I actually was talking with my students about this morning. I teach a class called the frontiers of synthetic media. And we talk a lot about what's going on in here, but I started with them with this image and I just asked them to talk about it. And they were quite impressed with how well the fur was rendered, the ear, these sorts of things. And we were talking about like, what does it articulate well and what does it struggle with? And we were talking about, like the chess pieces look like a melted mess, and the cat kind of looks more like a fox than a cat, maybe, or something like that. And they had really interesting things to say about this. For me, what haunts me about this image is this pawn all the way over here. So I play chess. I think about chess a lot. And this pawn to me is like this strange, impossible pawn. Like you can't really play chess and have this pawn get all the way over here without it turning into another piece or being captured or something like that. And this misplaced pawn to me is indicative of some of the things that I want to talk about today in terms of what can generative AI do and what does it struggle with? What does it do well and what are its limits? For me, the fact that it doesn't understand enough of chess to be able to correct this quote unquote error is indicative of some of the larger problems that I want to talk about today. We're going to talk about those issues by understanding a little bit more about the technical kind of protocols embedded into the technology. This idea of the operative moment, so how these technologies look when they're in motion, and what are their different components. So we're going to spend some time mapping it, and then by mapping it, hopefully start to understand how does something like this misplaced white pawn end up here, and more harmful things too. To give you a little bit of a sense of me, my dissertation was on facial recognition. I was looking at the triangulation between citizenship, the gatekeeping of citizenship resources and crises, and facial recognition to me is a tactic that kind of triangulates those three forces. As I started to give more talks and discuss facial recognition more in public, people started asking me more and more about deepfakes, and they started asking me more and more about generative AI. And I had already been sort of taking on artificial intelligence as it was incorporated into facial recognition. And so I'm coming at this through more of an image base that's now expanding out into kind of text-based understanding of synthetic media and generative AI. Part of this is part of this larger research project where I'm looking at the development of AI as a Canadian techno-national project. This started last year in my postdoc at the U of T, and I'm continuing on here. How has Canada invested itself in the development of artificial neural networks, the things that are powering things like generative AI, and how is this in particular kind of a Canadian history of these sorts of things? And I'm happy to talk about that in the Q&A or anything like that, but this is sort of the framework that I'm entering into this with. With this in mind, I did have some goals. I want to, I think first and foremost, develop some literacy and vocabulary for yourself, but I also think for your students to communicate with them, and maybe potentially for future interdisciplinary collaborations that you might feel a little bit more comfortable working in those interdisciplinary spaces. It's something I've done all the way through my career and found really, really useful. In terms of pedagogy, producing potentially effective evaluations and activities that address the current moment of generative AI, and again, we can talk more about that. This is probably the main argument that I'm going to make, that generative AI is a data visualization system. And what I've often found is if I can kind of speak to students about that and why that is, that generative AI is not generating anything, but rather visualizing the data that it's been trained on, something that I suspect most of us already kind of know. And we can explain how that works, which is kind of the goal of the talk today. I find that this then helps when we're thinking about how to make good evaluations, how to make good activities. And in doing so, communicate the strengths and weaknesses of this moment of generative AI. So I think things that Siddle and most of us that are teaching are top of mind. This is kind of urgent. So very quickly, I also wanted to thank Jay So, who is at TMU, and Adnan Nasser, who is at AceNet, both of which have helped me flesh out parts of this talk, both of which have helped me create generative AI systems, train my own models, these sorts of things, that when I came against my technical limitations, they were there to answer questions and things. And again, as a way of advocating for humanities scholars in particular to collaborate outside maybe their own immediate expertise with folks like AceNet, who are wonderful and marvelous. Okay, so how I entered into this is about 2020. I had a very early version of DALL-E, the kind of image creation software from OpenAI. And based on my face recognition research, I just started to do some prompts with it. Tell me what a Canadian's face looks like. And you can see it's light-skinned, male-presenting sort of face. Tell me what a citizen's face looks like. Well, again, kind of light-skinned, male-presenting faces. When I started to ask it more politically charged prompts, and I don't want to show the images and recirculate them, but you'll have to take my word for it. Like I put in a migrant's face. It was kind of definitely dark skin looking to camera, big eyes, kind of childlike. When I prompted it with a mugshot, it made a series of dark skinned, angry male faces. And so this is kind of, I think all of us sort of understand, even from the very beginning when these systems started to become public, that there is something in the visualization of their data that is pointing towards these harmful sort of logics. This comes from another article in November 2023 in the Washington Post. You prompt, this is stable diffusion, so not DALL-E, stable diffusion, but the same sort of computational architecture. A person at social services, and we can look at the types of faces and bodies that it generates, versus a productive person, and we look at this. And so I think this demands that we ask the question, like, where are these logics for the creation of these sorts of images, and we'll see examples in text as well, coming from? I think a lot of us understand that generative AI is biased, that it's harmful in these sorts of ways, but how does that bias get there? How do we get to these sorts of images? So really, I think it's worth thinking about the basics of an artificial neural network. So we're going to start with the basics of an artificial neural network and then talk about specific artificial neural networks, and sort of by diagramming and mapping them, hopefully understand them a little bit more. So a really basic artificial neural network has 3 layers. And within these layers, there's going to be other layers of neurons. So these neurons are these hyper-connected sort of nodes that are doing probabilistic decision making. So you have 3 layers, and again, within the input layer, you might have multiple layers of neurons. Each of these kind of neurons, rows of neurons, are dedicated to a task, so it kind of passes it. So you have the input layer, the hidden layer, and the output layer. So the input layer takes the data, so we can imagine another diagram, there's data here, and it kind of prepares the data for the machine learning that's going to take place in the hidden layer. So this is quite often used to standardize the data, that we're going to make it all the same size, all the same color, kind of transforming it in these sorts of ways. Passing all of that prepared data to the hidden layer. Now the hidden layer is where all of the deep learning is taking place. Depending on what type of neural network you're engaging with is going to be, the layers are going to be arranged differently. The layers are going to have different tasks. But I do find this idea of a hidden layer really evocative, right? Like there's something going on in this idea of hiding and hidden where most of the bulk of the work is happening. Then we get it kind of prepared for the artificial intelligence model. So that's basically the goal of an artificial neural network, is that we take in data, we do this deep learning, and then we output a model. So the output layer prepares this data for maybe a human viewable output. Yeah, we can talk a little bit more about pre-trained models in a minute. The biggest part of the jump in the state of the art of artificial neural networks. Artificial neural networks have been around as long as computer science has. The biggest, I think, jumps forward have been happening in the hidden layers, and in particular in the amount of hidden layers that are added into the deep learning process in combination with pre-trained models, which we're going to talk about. But early artificial neural networks really didn't have much going on in the hidden layer. They were pretty simplistic tasks. But now you will have artificial neural networks with like literally over 100 layers of really complex computation happening in the hidden layer there. So a simple artificial neural network sort of looks like this. You have training data. You pass that training data to an artificial neural network. And again, that artificial neural network is made up of input layers, hidden layers, output layers. And each of those input layers could in fact be 3, 5, however many layers it takes to prepare. The hidden layers, again, this could be 100 layers, output. And then at the end of this, we get an AI model, which is dedicated to a task. So we have sort of data. It's passed to this artificial neural network made up of these layers. We go through this deep learning process, which we'll talk about in more depth, but we get an AI model at the end. The AI model is what is imported into something like ChatGPT. So GPT, which we're going to talk about, is the model. ChatGPT is the app. So it's kind of, to me, you have to separate those two things. That GPT is the model, ChatGPT is an app utilizing that model. So if we think of this, kind of to wrap up this part here, training data, it gets passed to this increasingly high number of subtasks that it's going through in order to produce an artificial model that we can then include in something like facial recognition, ChatGPT, DALL-E, all these different things. So the biggest jump forward maybe is the complexity of layers within the hidden models. One of the other big jumps forward is the inclusion of pre-trained models. So this is where we start to get like almost like a nesting doll of artificial intelligence, in which we have, let's say, data that gets passed to an artificial neural network, but that artificial neural network is wrapped around a pre-trained model, a model that has already been through all the training, has completed kind of an effective version of executing that task, and we're asking to kind of fine-tune it. So you have a foundational model, right? And then you're sort of wrapping around another artificial neural network around it like a nesting doll. Really what it's doing is it's kind of fine-tuning that foundational model. You take that foundational model as a foundation, you add more data to it, you do more training, you add more layers around it, and you get a more complex model in the end. So pre-trained models are the heart of GPT. That's what the P in GPT is for pre-trained. So what we're going to start to see then is, okay, we have this nesting doll of artificial, like kind of building artificial intelligence models based on pre-trained artificial intelligence models. But when you start getting really complex, you start daisy chaining pre-trained models into each other. So something like DALL-E, an image creation synthetic media, generative AI, is actually kind of putting two artificial neural networks together, which we're going to talk about and sort of map. So when we start to actually map this, I think it's useful to think like, where is the data? How many multiple sites of data are happening? If you have a pre-trained model, you have the data that goes into that pre-trained model, plus the data that's being used to fine-tune, for example. And then what happens when we daisy chain it into another kind of artificial intelligence model pipeline? So this, I think, will make more sense when we look at something like DALL-E and we talk about how a convolutional neural network, for example, talks to a diffusion model. If you're interested in further resources, this book kind of talks about, I think, bridges a really good technical discussion into discussions about political power, bias, errors, hallucinations, these sorts of things. I teach this from this book. I think this book is excellent. This is my postdoc supervisor, Beth Coleman. This project kind of trains an artificial intelligence model on Octavia Butler's writing and thinking, and to create images, these texts. This project is really, really interesting. This one isn't in the Munn Library, but I know that Talking Nets is available through the Munn Library. It's an oral history of neural networks that I find actually quite interesting to hear computer scientists talk about kind of the history of how they came to their discoveries. And it tends to be a little bit more accessible, frankly, than if you're just trying to read like computer science papers. So if you're thinking about how to teach maybe students, folks that don't have the technical knowledge, which is where I am teaching, I'm in a communication media studies department, I find texts like these really interesting and useful. The other one that I would point to is this really magical work that I love from F. James in the early 90s that really kind of explains exactly what I just did about artificial neural networks, but it has fun drawings and diagrams, and it's basically like a slide deck. And this, if you just Google Introduction to Neural Networks, a PDF will come up right away. And again, I found this like a very, very accessible thing. I used it today in my class actually with students to talk about similar sorts of things. And even when we're starting to look at, why are people excited about artificial neural networks? He's explaining it and then he's doing diagrams and these sorts of things. So really part of when I was talking about the development of AI in Canada as a techno-national project, and this kind of, when I talk to other computer scientists, I shouldn't say other, I'm not a computer scientist. When I talk to computer scientists, they lament that artificial neural networks are essentially like the de facto methodology of machine learning now. And when a lot of them that were working in the 60s and 70s, there were many ways to think about artificial intelligence, and they were trying out all these different methodologies, and eventually almost everything has homogenized into artificial neural networks, in part because of what James is saying here. They're inherently parallel, so when we look at those dense networks of neurons firing, they can do multiple tasks at once in sort of all sorts of directions, that it's not necessarily a linear pipeline. And that, more than anything, they're good at solving problems, or at the very least appearing to solve problems. And we might ask ourselves, what problems are they better at solving and worse at solving? The other thing is that this idea of deep learning, like aside from an artificial neural network, when you start instituting deep learning within artificial neural networks, you don't have to feed it examples, it is learning. And we're going to talk about this idea of backpropagation, in which the system kind of generates feedback for itself, feeds it back through, and goes through. So a human doesn't have to keep adjusting it, it essentially cycles through until it learns. What it is good at is places where there is a lot of data and that data is really stable. So it is pretty good with the weather because we have a lot of weather data to go back on and train, and that data is pretty deterministic and stable, right? So in Canada, it makes sense that some of the early AI was machine translation, because we have a Canadian Hansard that is perfectly bilingual, weather, because we have a lot of weather data, and usually by tracing the data, you can find what is AI good at and what does it struggle with. So we're going to talk about that. It's funny, he says fault tolerant. It is, right? In the sense of if it doesn't know something, it makes something up. That there is this certain sort of, it doesn't just quit. It doesn't just stop when it gets to a certain point about knowing an answer or not. It's actually quite tolerant. It'll either say, I don't know this, or make something up. For anybody who's coded, how finicky actually kind of going line by line code is. To have a system that doesn't just shut down when you make an error is interesting. In this one we could talk about this idea of traditional programming going away. I think we're definitely starting to see that in the contemporary moment. So really what I want to talk about is transformer neural networks and convolutional neural networks If we have time, we can talk about generative adversarial networks, but I think these two are probably what's going to come up most in our classrooms, and in particular transformer neural networks, which are used for primarily text-based synthetic media. Convolutional neural networks, I came to them through computer vision and basically matching images to text labels. Right now it's being used within something like DALL-E to change a text label into an image. And we'll talk more about that, but computer vision sort of at the heart that is being remade through this daisy chain of artificial neural networks into image generation synthetic media. So let's talk a little bit about, pause for water, ChatGPT. So GPT, again, stands for Generative Pre-trained Transformer. So we're basically making a model, an AI model, which is called a generative pre-trained transformer, and then we drop it into an application, in this case, ChatGPT. So what does a generative pre-trained transformer model look like, and how does it operate? So if we step way, 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 way back, and we do kind of like a bird's eye view of something like ChatGPT, right? We put in a prompt, right, an academic essay about Romeo and Juliet's star-crossed love. We have within the system an encoding process in which it's quote unquote kind of reading. It's taking it into the system. Then we have a decoding process in which it's writing the prompt. And then we get the results, this kind of like human readable essay about Romeo and Juliet's star-crossed love. So that's kind of like the simple bird's eye view of it. Let's start to make that a little bit more complex. So within ChatGPT, this is sort of the GPT. This is the AI model that's being dropped in, right? We have the prompt. We have this process of tokenizing, which I'm going to talk about in a minute, which is essentially breaking up the words into machine processable kind of smaller parts, right? And from that, we're encoding the prompt. Basically, the system is taking it in and comparing it to and working through what it knows from its AI model in order to decode. Now, the decoding is a prediction. Everything in AI is predictive. Everything in AI is based on statistics and the statistically most likely answer. So it predicts what the answer is, and then we surface it, in a way that we can read it, essentially, like in the app itself. So everything in AI is about prediction. These transformer networks are the exact same thing that's in your phone when you're typing and it tries to guess what the next word is. That is essentially the same sort of thing. GPT is much more complex, but it's the same sort of idea. It's kind of jumping ahead. Based on what I know, here's what I think is coming next. So we have the prompt, we have the encoding and decoding, the results. But this encoding and decoding comes from the building of a transformer neural network, which requires data. We pass it into this neural network. We generate a GPT model. We drop it in, and it's the model that is kind of doing this. But you can start to see this is getting like a little bit more complex. So in terms of tokenization, we'll maybe talk about tokenizing first, and then we'll talk about the AI model and the encoding and decoding. So this is what it looks like in the tokenizing process, the kind of like a visualization of it. So this is the system kind of taking the input text, let's say, and starting to chop it up into machine processable, algorithmically processable kind of ideas. You'll notice sometimes it does it mid-word, sometimes it lets the whole word, it's kind of making sort of decisions around sense and ideas of reading that maybe a human wouldn't. And the thing to understand here is that this is purely informational, that is the goal, to translate this into kind of like numerical data that can be processed algorithmically. So this is that kind of like first stage of tokenization. Then it gets passed to this GPT pipeline. So I wanted to talk a little bit more about that and what it looks like. So if we look at the first part here, data, where's the data coming from? One of the things that we do in my class is just this provenance exercises around data. Where did data come from? In this case, using this Common Crawl database, which is this massive open source database, petabytes of data basically collected by scraping the net and dumping a bunch of things in. This is one of the things that is worth noting right now, that the first limit of something like ChatGPT is, when does the data stop? So if you stop collecting data in 2020, and then you train a model based on data that stops at 2020, the model is essentially going to be limited by that date. Similarly, if you train a model in 2020, that knowledge is kind of frozen in time. So there's going to be versions of like AI models, let's say, that were trained earlier that still think like Kim and Kanye were married still. That it is this sort of like trapping it in amber. We should be asking, like, what's in this stuff, right? And maybe that's something you can take up with your students. It's definitely something that I encourage in my class and that we actually do, where we go into the white papers of stuff, we look at the data set, then we actually go find the data set, look at the data set, who put it together, what's inside it, these sorts of things. It's activities I can talk about more in the Q&A. Okay. This is where it starts to get a little bit more complex. So if you just kind of stick with me. So this is that kind of middle part, the transformer neural network. Here's the data. Now we're going to pass it to the neural network. So we have this data. We're tokenizing the data. We're encoding the data. And then really this is one of the other major leaps forward. We have this idea of attention. So when it is encoded, and tokenized and encoded, we are trying to preserve a sense of the word and the order. But what has been this leap forward in something like transformer neural network, this idea of intelligence, is that it directly models relationships between all words in a sentence, regardless of their position. Meaning, it does not read left to right, top to bottom like a human. It is doing this mathematical process in like nth dimensional space, in which it is trying to map the relationship of all those tokens to each other. So it's not a linear process. It's in fact kind of doing these multiple parallel kind of mathematical equations all at once. Which is, it's really interesting if you start to read about it. One of the major papers is called All You Need Is Attention. That's one of the major kind of like sets this out here. That is quite good. At the end of this, we produce a score or value. Based on that score, we predict what the answer is, and then we give an answer. So we kind of have data, tokenizing it. We're trying to preserve an order of the words. We pass it to this kind of like attention sort of set of layers that are going to start to recognize the relationship between all the words and tokens at once. And then we get a prediction. And then you'll notice the system kind of like has an answer and takes that answer and goes back to the start with it. This is kind of this self-feedback loop. So basically that's called backpropagation. So every time we go through a loop, that's called an epoch. And how we get through that loop is backpropagation. So an epoch, when I was training an artificial intelligence, like a generative adversarial network, we would do 5,000 at minimum. You're constantly kind of cranking through these things in sort of brute force. The more complex the model, the more epochs we're going to go through. This idea of backpropagation, Adnan came up with a good definition for me here. It's like a coach teaching a player how to improve their game. When the player takes a shot and misses, the coach gives feedback on what went wrong and how to adjust for the next shot. In a neural network, backpropagation works similarly. It measures the error of the prediction, delivers a message back through the network on how to adjust, and then we do it again. And it's this sort of like loop of feedback. That one loop is called an epoch. This article, again, if you're looking for things to show your students, I found this article in the Times quite useful. It visualizes, oh, that's nice. I don't know if I'm logged in, but basically you can go into this space and see this is what it starts with. And then as you give it more epochs, 250 rounds, you can start to see that it gets a little bit more legible. And it kind of goes through and you can choose different people, Shakespeare, these sorts of things. But this is like, I think, a really interesting visualization for students and different people about like how many epochs do you need to do? How much computational resources do you need to do? Because part of how I've been making the argument around generative AI and when to use it and not use it is also environmental. These things take massive amounts of electricity, draw massive amounts of water, in part because they are just churning and churning and churning through their machine kind of algorithmic processing in these AI models. I hope this doesn't start at the beginning. Oh, good. Okay. So, to review, we have this kind of simple bird's eye view, prompt, encoding, decoding. A little bit more complex, but then when we sort of pull all the way back, this is what we end up looking at, right? We have this input, we have this tokenizing, right? We're breaking the words up into algorithmically processable units. We're passing it to the AI model, which is made of data, petabytes of data that is passed to this transformer network, which itself is this kind of like trained by looping all the way through this to give us a model which we import into encode, decode in the output. So one of the things that I do when I kind of arrive at this with my students is ask, where do you think the vulnerabilities are? Like when we start to talk about errors, hallucinations, these sorts of things, you sort of look at this map and you ask yourself, like, where might bias intrude? Where might human error intrude? Where might machine learning produce errors and things like that? One of the most obvious sites, I think, unless, Melanie, do you have a guess or anything? No. Data, right? This is the classic sort of garbage in, garbage out. So if we have bad data, we're going to get kind of a bad output. But I also think the way that we're training neural networks is going to produce a very specific and limited type of way of encoding and decoding. That, again, what it is a probabilistic predictive system that is reliant on things that look nothing like language when they're actually in the system and being processed. This goes back to like a really rich history in artificial intelligence around an argument around like, just like, how do you make artificial intelligence? And for most people going back into the 40s, it was a replication of the biological brain, and the biological brain takes in information and outputs behavior, right? And so long as that is kind of encoded into these systems that, thinking, reading, writing is a kind of mechanical informational process that's been externalized into these systems, we're going to end up with problems when we start getting into squishier, less deterministic sort of applications of these technologies. It's good for like chess or checker, things where there's set states of rules, things are pretty stable. But when you start stepping outside of those sorts of things, and increasingly that's sort of what we're asking these systems to do, they struggle. So this GPT model, and again, kind of the chat GPT, this is for text-based, primarily for text-based. Let's talk about something like DALL-E and image-based. So this is something that I again, kind of work a little bit more often with than text-based, but I think is really useful. So DALL-E is dependent on this CLIP model, contrastive language image pre-training. So again, another pre-trained model. So when we're thinking about generating an image, we give it a prompt, a text prompt, make me an image of a corgi playing a trumpet. Similar sort of thing. We get this encoding, we get decoding, and then we get an actual image, right? The encoding and decoding, as we'll see, are different, and I would argue probably a little bit more complex than some of the textual stuff because you're doing both images and text. But the basic idea of text prompt, make a prediction about what image should be associated with that text prompt, generate the image is the same sort of thing. It's still the same sort of predictive system relying on artificial neural networks. So we have this slightly more complex pipeline in which we have the prompt, we're tokenizing and encoding that text prompt, then using that prompt again to kind of generate an image that it predicts is associated with that prompt. But when we start to see, okay, what is the AI model doing this encoding and decoding? We have this training data. It's passed to, I kind of separated these, but essentially CLIP is working on a convolutional neural network that the job of this is to associate effectively text with images. And it's actually the training data when we look at it are pairs of text and images. That's what it's using. It's not just images on its own or text on its own. It's actually pairs of text and images. So its job is to associate certain text with images in a probabilistic way. That gets passed to the diffusion model. The diffusion model we'll talk about is the thing that actually makes the image down here. So it's a little bit more complex, right? And this convolutional neural network comes from a long history of pattern recognition, object recognition, and computer vision. So let's have a look at this. This again starts to get like a little bit hairy a little bit quickly, but it's interesting, I think. So this CLIP model, the contrastive language image pre-training, a staggering amount of data, 400 million image text pairs. So again, we might ask ourselves, some of those pairs are machine generated. Some of them are going to be human annotated, like you pay a bunch of people to look at images and attach text tags to them, right? So, but that's the data set. So ImageNet, which was being used in like the 2010s, not that long ago, 15 years ago, 1.2 image text pairs, we're up in a massive way, exponential way to 400. So this is one of the other kind of leading causes of the kind of advance of state of the art in artificial intelligence is this exponential increase in the data that's going into it. This is also something that's worth flagging, again, for students if you're making arguments around this. It took 2 weeks of what are essentially like the biggest processors you can use, working in tandem and just churning through for 2 weeks in order to produce the model that then generates this. An incredible amount of resources that go into this, right? So, how do we get, again, text image to an actual text? So this is where we're starting to daisy chain two things together. We're actually daisy chaining kind of this CLIP model, a convolutional neural network, into GLIDE, which is a diffusion model. So again, we have to imagine the AI model kind of like cycling through all of this. And it might even like cycle a bit through this and cycle a bit through but basically artificial intelligence is trained by loops upon loops upon loops. So we get this text prompt, we encode the text, we're breaking it down. This is sort of, again, what a convolutional neural network is. It's doing its best to match text to images. We're training a model to match text to images or images to text. That's what convolutional neural network is, and creates pairs. It's those pairs that are then passed to the generative, the quote-unquote generative model. In this case, a diffusion model. And it's the diffusion model that's actually producing an image of the text prompt. So again, this kind of like daisy chaining. Let's also remember, like, just like GPT, within that, we're incorporating in a foundational model and then wrapping more artificial neural networks around it. The same thing with CLIP. It's actually trained on a foundational convolutional neural network that we're then wrapping more of that process around. So in terms of matching the text to potential images, right, we're going to use what's called a convolutional neural network. Now this, I don't know. Like I can kind of walk through it, but I want to be able to give resources for people to go back to this and talk about it. This diagram I find quite useful here, right? Basically, you have a convolutional layer. So what they're doing is reducing, kind of the quality of the image, down, 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 down. And as we're doing that, we're taking the parts of the image and we're making kind of, by reducing it, making it more probabilistically stable. A big image like this is very complex, but if we start to reduce it, we can start to make better guesses about it. is sort of the assumption within this system. So we kind of reduce. It's called pooling, right? And then we kind of pass it into this layer that is trying to basically associate a text with an image and give a score, right? So we have this image here, we're reducing it, we're passing it through this system that then guesses, oh, this has a 0.1% chance of being a dog, let's say, or out of 1, 10%, 20% horse, but 70% zebra. And so it's making the prediction. And basically what it's doing is this image now has this text label, predictively. I'm going to predict that this image has a text label. So that's the main job of this convolutional neural network, is to build associations between texts and images so that when we give it a text prompt, it can start to associate it with images. Yeah, Melanie.
Does this work similarly to what you described with the self-attention and the other like with the text-based models? Like is it reading each of those kernels all at the same time? If I'm looking
essentially, right? Like it's not like it scans. No. So when I first started building face recognition, I was using HAR cascades. They don't necessarily do things linearly, but it was kind of like an older bespoke way of doing computer vision where it was a little bit more like that. It wasn't linear necessarily, but it definitely was less. It was almost by like comparing pixels to each other, and then you say like, okay, based on this comparison of pixels, here's where the face is most likely to be. This is a little like, this is all math. All of this is like kind of human readable visualizations of this stuff. At no point is like the system kind of like dealing with quote unquote images or text. It's actually dealing in the way that you're talking about these parallel tasks at once around informational objects. Does that make sense? Yeah. And then these kind of the ends of the pipelines are the kind of human readable stuff. That's the things that we would kind of say image and text. Good? Yeah, thank you. Oh, this is just a bigger version of it, but the same sort of thing. Right? So the goal of a convolutional neural network is to associate an image with text and create pairs of those two things. Okay. So once we have like an AI model that's quite good at linking, let's say, text to images, now we're ready to pass it to something that can actually make an image. So in the case of DALL-E, I was looking through the kind of like the white papers and the explanation. They're using something called GLIDE, which is a diffusion model. To be honest, this is where I start to run up against my my limits of kind of like mathing and computer sciencey stuff. I feel like I understand this very broadly. So if there's anybody in the chat or anything like that can take a better stab at explaining diffusion, basically what it's doing is we've kind of encoded these pairs of image and text, and it's the GLIDE model that's decoding them into the image themselves. Basically what it does is, so a full diffusion model starts with kind of static and noise. It creates an image from that static and noise, and then breaks it back down again into static and noise. And then part of it is just looping through that kind of like static and noise to image back to static. That's a full diffusion model. In something like GLIDE, we don't need that full process. It is sort of like half a diffusion model. So basically, you start with noise and you create the image. You don't need to go through the whole process of turning it back into noise again. You stop at that kind of like half diffusion model. So we get the text image pairs from CLIP, from that convolutional neural network. We embed it in, we start with this image of noise, and then we kind of like reverse noise. And again, this is where the limits of my kind of like math and engineering come in. There's all sorts of methods for denoising an image and things like that, going backwards along a Markov chain. But again, I'm sort of running up against ways for me to explain it. It's something I need to spend more time on. But based on these text image pairs, we can sort of say, okay, this is the text. Here's the image that I want to create out of this kind of image that starts as, let's say like a 256 by 256 image of just kind of noise, cranking through, doing these kind of mathematical calculations based on the text that we're trying to create, and it produces an image. Oh, I just said this, yeah. Recognizing the specific noise patterns at each step and denoising the data accordingly. So again, this kind of like half a diffusion model, a full diffusion model. Okay, so again, this is sort of the more complicated version of what's going on in DALL-E at the AI level, is sort of this pipeline that is in fact kind of this convolutional neural network in which we're doing that kind of like pooling, reduction, making that predictive score, passing that predictive score to the diffusion model. This is where we're denoising until we get to the image that we want. So if this is sort of kind of like the simple version of DALL-E, again, kind of going back to the start of this, we're encoding, we're decoding, taking a text prompt and then making an image at the end. Here is what the kind of more complex mapping of it looks like, in which we have kind of like, again, this quote unquote simple pipeline. But how do we get to that simple pipeline? We have these text image pairs as data, our training data, fed into this deep learning sort of pipeline that is this combination of the two models. We get the model, we drop it in, and then we get this. So this is something I did today. I'm writing a chapter on sort of what happened to face recognition during COVID. And the short answer is, for a time, it broke a lot of face recognition because face recognition was used to having the whole face and the whole face as kind of this machine processable object. So what they ended up doing to solve for masked faces and facial recognition is they started to synthetically make facial databases. They started to computationally add masks to facial data sets. What I've been finding in my facial recognition work is that databases that were initially intended for facial recognition have leached over into generative AI. So I just had an article come out talking about how like a mugshot database, when I started talking at the beginning of this talk about like why on earth do we have, when I give a generative AI system the prompt of a mugshot, do we get these angry dark-skinned faces? It's because quite often they're relying on these mugshot data sets, which are overpopulated for different policing practices, any number of reasons, with young Black men, basically. And part of my research into facial recognition is to explain that. Here, I was really curious. Like, these prompts were quite general. I just said a city of people wearing masks for COVID. And these are the images that came out of the system. System's called Stable Diffusion. And it was curious, right? Like I don't really have an answer for it. Like I literally did this afternoon because I'm working on this chapter. But we can start to see this as a visualization process. Like this is what it's predicting based on my prompt I want to see. And it looks here like we're in, I don't know, Tokyo, somewhere maybe in Beijing. I'm not quite sure. I can read some kanji and things like that in the Japanese sense, but I can't read in any other way. It's interesting, right? And I wanted to leave this as sort of a final sort of argument for these systems as data visualization systems, not generators, and as a way of producing maybe conversation. I know we have 10 more minutes kind of talking maybe about the things that we started with in terms of goals, literacy, evaluations, activities, communication with students, these sorts of things. Okay, great.
Can you hear me if I just ask a question?
Yeah, I can hear you.
Okay. Okay, it's a bit disturbing, sorry. I had a question about the training data text image pair thing that you're talking about. So those, I suppose I'd just like some clarification on what that looks like. I mean, is it something as simple and discrete as like bucket and then a picture of a bucket? Or are these long strings of text descriptors that are attached to more elaborate images that are then used as training data for that purpose? Thanks.
They, I speaking generally, it's more like the first than the latter. Like they are kind of like, I don't know why I'm talking to the speaker. Okay, the voice got up there. Like images text pair. They might have multiple text pairs, right? But if we have longer strings, they become harder to compute. They become computationally more difficult objects. So I find the pairs to be as brief as possible. You might have multiple, like an image with multiple annotations on it, but I find the annotations to be like deliberately kind of concise. And this is where you start to run into issues, especially if they're human generated pairs of images and text. There was a Trevor Paglen, Kate Crawford did something called ImageNet Roulette, which used ImageNet and basically surfaced a lot of the pairings. And so you'd end up like you could upload an image of a woman and it would like have all these derogatory terms for a woman because they'd been kind of human generated text image pairs.
Right. Okay. Well, thanks very much. Appreciate it.
Yeah, no problem. Thank you. That's wonderful. Thank you, everybody who came. I really do appreciate it.